All right, so important example 18. Yeah, what just you can review we did yesterday, but just a reminder that what we did, finding a general solution, then using an initial condition to find the particular, only to turn around and plug in another value of x to get what we wanted. It worked. It just relied on us being able to find the antiderivative. So the reason this example isn't so important is because if we can define it as a definite integral, which we will, we can still do it by hand, but in the event that it can't be done by hand, the calculator can do it, even if it's just a number cruncher, not a computer algebra system. So anyway, let's go ahead and review this, right? What you have now is a function of what you started with plus your net accumulation over that interval. Okay, so that's what this is right here. F of B is f of A plus the integral from A to B of your rate equation F prime. And that's important that these values line up, right? F of A is your starting value. It doesn't have to correspond with zero, but it is your starting value or something that you know about the original function at a given time. And it corresponds with the input on the bottom. And then a B is what you're trying to get to, and that's the upper interval of integration. So look how we can write this one now. And this is how we know that it's going to set up as a definite integral. I'm trying to find f of 2. So I'm going to come over here and say, okay, what is the function value of f at 2? Well, do I have an initial condition? I do. They tell me it's f of 0. So if I start at 0, I wonder what f of 2 is. Well, it's where I started plus my net accumulation from 0 to 2 of my rate equation for f, right? That should be the same thing. Your rate equation, is it given? Well, it certainly is, right? So notice that I can set this up now. This would be kind of my template. You would get a check for this and a check for the f of 0, okay? And now if I plug it in, let's see, they did tell me f of 0 was 5, and it's plus then the net accumulation from 0 to 2 of the rate equation, which is 2x squared minus 2 dx. So that's another way to set it up, okay? I like to set it up with the notation first, because then I can clearly see on the function notation my inputs, and I can line them up to my intervals of integration. I could do this by hand pretty easily, right? It's a real simple definite integral, but I'm not going to because we can. I'm just going to go straight to the calculator now. So 5 plus math 9. So here's another reason, again, why we do the definite integrals on the home screen. I can add 5 to it right there from 0 to 2 of 2x squared minus 2 with respect to x. Now, this calculator is a number crunching machine. It's not finding the antiderivative and then evaluating it like one with the CAS, a CAS system, we call it, computer algebra. So I should get 6.33333. And I do. Well, looky there. Wow. So which method is correct? Both of them are, right? Both of them are correct. But the one on the right does not rely on being able to find the antiderivative because it's doing it numerically, right? Pretty powerful. Pretty powerful. So I was finally able to make 5 questions then. I put them in AP Classroom, but I'm not going to have them due until Tuesday at noon. So you got plenty of time to do those 5 questions. It's called 4.2 and 4.3 part 1. So you'll see there. I think there's like one or two questions like this. Make sure you look for the calculator icon, because that means the answer can be used with the calc, or the question can be used with the calculator. If there's no calculator icon, no, don't do it with the calculator. Like this one could be done with or without a calculator. All right. Awesome. So let's try it out now on example 19. Kind of the same idea. If f prime of x is 4 sine squared of 2x, so it's a derivative equation, and f of 2 equals -2. There's an initial condition alert, right? It doesn't correspond with 0, but it is an ordered pair that satisfies the antiderivative of f prime. Bless you. Use your calculator to find the following. Well, f of 3. Now I could, if it didn't tell me to use my calculator, I could still do it if I wanted to and was able to using method one up here. I could find the antiderivative and find the value of C by using the 0.2 -2 and then plug in the 3. But what's the antiderivative of 4 sine squared of 2x? We don't know what that is yet. And even later, when we do know what it is, you would have to use a power reducing identity to turn sine squared into a cosine of something. So it's not going to be fun. So let's see if we could do it using a definite integral. So here we go. We go f of 3. I'm just going to rewrite it down here. In other words, the y value at 3, where we are at 3, or what we have at 3, is equals a function of the y value we started with. We started with f of 2 plus the net accumulation from 2 to where we're trying to get 3 of the rate equation of f, which is f prime of x. There it is. There's the setup. That's like a 2-point, that's 2 checks. Check, check. You get a check for the integral. You get a check for the adding the initial condition. There's only one check left if this were a free response, and it's the answer. Wow, we barely broke a sweat. We don't really even have the answer, but we get 2/3 of the points. That's how important the setup is. So I did leave the tray open for your scratch work for those problems. And it does say put any calculations and any integral setups. Okay, so make sure you always have it written on your paper or iPad before you pick up a calculator, whether it's a multiple choice or a free response. This is what I mean by an integral setup. Okay, integral setup. All right, now if you want, you can make it more appropriate or specific for the problem. What is f of 2? It's -2 plus the integral from 2 to 3. What's f prime of x? Well, it's 4 sine squared of 2x. Either one of those would give you the 2 checks for the setup. The first one, I think, is just a little bit easier. Now, because I want to do this multiple times for A, B, and C, I don't want to have to type in the function repeatedly. So this is a good time to consider putting into y1. Now let's do that. That's no mean feat. 4 sine squared of 2x is the same as 4 parentheses sine of parentheses 2x. Close it for the angle, close it for the trig function, and then square it. That's how you want to type it into the calculator. All right. Make sure you add those extra parentheses. There's no way on the calculator to type it in as sine squared in the condensed notation. And we should be in radian mode, which hopefully you are. Let's check. Yeah, radian. Good. I'll go to y equals, type it in 4. I'm opening a parentheses. Sine, it opens it, 2x. Close it for the angle, close it for the sine, and then square it. Right. Now, I really don't care about the graph. I'm not interested. I just want to recall it. So now I'll go to the home screen, flush, right? And by the way, if this were truly a free response and you put your equation in y1, here's what you might want to do. You might want to, it says f prime equals, you might want to also just relabel that as y1, just so you know where it's at. And then in that case, if you're trying to help yourself, you know, maybe you want to put in the -2 because that number you actually have to physically type in, but you're not going to get bonus points for actually writing in f prime into the integrand. In fact, if it's multiple terms, you can really lose points if you don't put parentheses. So this is a more helpful version for us. So -2 plus math 9 from 2 to 3. And then I recall it alpha trace number 1 with respect to x. Hit enter. And there it is, -0.762 or 763. What? Why is it negative?
Your answer in the calculator is
Oh, crap. Thank you. Thank you. Yeah. I was like, what? I would have just lost a point. Yeah, I would have lost only 1 point though, because I had my integral set up. Yeah, but we're going to want all 3. Yeah, good. I don't know why I put a negative there. I guess I'm just in a negative mood today. Yeah.
Just say no.
Yeah, just say no. Yeah, no, I'm in a good mood. All right. F of 5. Hey, F of 5. Well, let's see. What we have at 5 is a function of where we started, which is still F of 2, plus the net accumulation from 2 to 5 of my rate equation, dx. Now, that would be really all you need to show. I know what F of 2 is, though. It's -2. So if you wanted to rewrite it like this, you can. I don't think these questions necessarily would come back to back to back like this, but yeah, I'm going to go ahead and just type it in. I'm not going to even recall it because I need to practice, right? -2 plus math 9, math 9, math 9 from 2 to 5 now. Ooh, 5 of whatever's in y1 with respect to x. Big bucks, no whammy. Now, don't tell me. +4. Thank you. Good. 0.038. There we go. That's the net accumulate. F of -2. All right. So what I have at -2 is a function of where I started plus the net accumulation from 2 to -2 of f prime of x dx. Now notice this one is a little bit interesting because I'm integrating from right to left. Yeah. From 2 to -2. There's no real reason for me to flip to the intervals of integration and put a negative out in front of the integral. It is what it is. I've set it up. The calculator will give me a number that basically is me working back in time. And I'm not even going to rewrite it because I don't have to. I know what f of 2 is. It's -2 plus math 9. Getting used to the old math 9 thing here. From 2 to -2 of alpha trace number 1 dx. Boom. Okay, -9.010 if you truncate, and I'm a big truncator. Okay, so any one of these three calculations, you might ask to do on a free response. And what happens quite a bit is you're also asked then to write an equation for f of x at any value of x. Okay, and sometimes it comes like this, where you're doing concrete examples first and then you're generalizing it. But sometimes it comes the other way around, where you write a general equation and then you're using it. Okay, I did it this way first so we can kind of use our pattern. Write an integral equation for f now at any value of x. Well, what's changing from one problem to the next? F of 3, the only difference was that was a 3 up there, yeah? For f of 5, the only difference was that was a 5 up there. F of -2, the only change was that was a -2 up there. So in general, what should it be for any x? F of x then should be where I'm starting, f of 2, right? Plus the integral from 2 to x, yeah, of f prime of x dx. Okay, now here's the one exception. I don't want to stop here as my final answer because I'm not evaluating it. I'm trying to present a function that can be used repeatedly. So this is not necessarily considered a numeric answer. I do want to replace f of 2 with what f of 2 is, and I do want to replace f prime of x with what f prime of x is. So when you're presenting an integral kind of like as here's a nice usable form, you don't want to have essentially abbreviations in there. So I'm going to set it up that way because it's easier, but now I'm going to substitute in. So this is -2 plus the integral from 2 to x of, and now I'll write sine squared of 2x. There's a 4. Oh, there sure is. Thank you. Yeah, so there is a 4. I can pull it out in front of the integral if I want, but I'll save that for someone else to do. I'll let this guy ride in the cab of the truck today, right? Instead of in the back. Thank you. So this then would be the answer that we'd want to present as our final answer. All right. Cool. What would f of 2 be? using this, what would f of 2 be? Well, f of 2, yeah, good. It would be -2 plus the integral from 2 to 2, which is what? Yeah, it's 0. So it's just -2. Oh, okay. F of 2 is -2. Oh, yeah, they told me that, right? That's what they told me. But it's a good check, right? It's a good check. Hey, and now that we have a function of x right here, what would f prime of x be? Well, what's the derivative of the constant -2? 0. And then what would be the derivative of the integral from 2 to x? Oh, I'm glad I did this because there's one thing I need to do as my final answer.
Plus C.
Not plus c. No. This is f of x, remember, and I want that to be the only thing that changes, right?
Oh, gee.
Oh, crap.
Sine of 2x.
Well, yeah, I don't want that x to be considered part of the independent variable, do I? I don't want this x nor this x here to be considered part of the independent variable. So, what do I have to do? I need to change that to any variable other than f or x.
L.
Okay, to L dl. There you go. And then I would do that down below as well. I wouldn't need to do that above because that's not my final answer. But if you wanted to, you certainly could as well. All right. I'm glad I caught that because that's another reason why we want to make sure we put it with the actual equation in there. So you could lose points. Now what's f prime of little x? Well, it's 0 plus, and now what's the derivative with respect to x of 2 to the x of that? It's just that, right? 4 sine squared of, and now it turns back to in terms of x, right? Based on what we did yesterday. 2L dl, 2P dp, 2T dt, just not f and certainly not x. Okay. All right. There you go. Super important example. All right. So here's a little taste of section 6.3. And by taste, I mean, yummy, raw sewage. Bless you. Maybe that's a bad word, right? Here's a taste of raw sewage. So, I'm sorry, not 6.3. It's a taste of 6.1. In 6.1, what we do is we just look at old free response questions that dealt with this important idea, number 18. But most of them are in word problems. So we have context here with units, but we don't really need units to do it like we did up above. All right, calculate permitted. Raw sewage, which is leaking. I don't know if the bathrooms in the rest of the building are working, if they got it fixed. Okay. Raw sewage is leaking from a storage tank at a rate given by this. Now notice that this, it said, is a rate equation, but it's not listed as like S prime of T. It doesn't have to be listed as a prime. It's a rate equation. S is measured in gallons per hour. There's another way to verify it's a rate equation. And T is measured in hours. If at T equals 2 hours, there were 572 gallons of raw sewage. Is that an initial condition alert? Yeah. And again, it doesn't mean initial like corresponding to T equals 0, but at T equals 2, we know there was a certain amount in there. All right, part A. How much sewage has leaked out of the tank from 2 to 5? Now, when we want to accumulate sewage, if we have the equation gallons per hour, how are we going to get from gallons per hour to gallons, which is the units we want on part A? Do we divide or multiply? Multiply, good. When you have to divide to get your units, it's probably the derivative, right? When you have to multiply, it's probably the integral. So the question here is, I know I'm going to have to then leave a little space in front. I know I'm going to have to integrate from 2 to 5 of my function S of T dt. And that's going to give me gallons per hours for S times units of dt or gallon or hours That gives me gallons. The question here is, do I want to add the initial condition to this to get the answer to the question, or is this not involving the initial condition?
It doesn't involve.
Did you say yes or no? It does or doesn't? It does not. Good. This is just what's the net change in the sewage in the tank, right? How much has leaked out? If it asks how much is in there at time 2 or 5, sorry, then I would need to add the initial condition. So that's the careful reading. This one is not what is it at the moment, but what was the change over the interval. So it's just the integral. All right, so now that I have that, let's label our integral. I'm going to call this sewage. All right, sewage equals the integral from 2 to 5 of S of t dt. Now, because it's a calculator question, once I get it set up, I'm going to go to y equals, get rid of that one, and I'm going to type in the equation. Negative e, which is second ln, to the square root of, again, I use x here. Double check, triple check, it looks good, boom. And again, if you put it in your calculator on y1, let's call it y1 up there as a reminder to ourselves. All right, so now I've gotten a check for this integral setup, and now really I just go straight to the calculator for the answer. Math 9 from 2 to 5 of, recall the equation, alpha trace 1 with respect to x, and I get negative 19.722. Yeah, the rate is gallons per hour. And so this is going to have units of gallons. And now I want to answer the question. So what does the negative mean? The negative means that the sewage was decreasing, right? I lost the net change. The net change was negative. So if it asks you how much sewage leaked out, you don't want to leave that as your final. It's the positive value. So 19.722 gallons leaked out from t equals 2 to t equals 5, bless you, hours. All right. All right. So that was just a net change. All right. Part B, how much sewage was initially in the tank when it started leaking at t equals 0 hours? Oh, crap. Someone should have probably known how much was in the tank, but we don't know. Someone finally went in there and measured how much was in there 2 hours after it started leaking. But can we use math to extrapolate back in time? Sure we can. Yeah. Now, is this one going to involve adding the 572 to it? Yes. Whenever you're looking for how much is there at this time, or how much do you have at this time, or where is it at this time, that always involves the initial amount. So again, I'm going to call this sewage. It's the initial amount, and by initial here, we just mean what there was at 2. Now, can I call this S of 2? Is that an appropriate label for the amount of sewage at 2? Very good. S is a rate equation. Sewage could have been S, and then the rate equation could have been S prime, but that's not how they labeled it. I don't have a name yet for the amount of sewage in the tank. They labeled S as a rate equation. So in this case, I'm not going to make one up. I'm just going to write the number 572 there. Okay. So 572 plus the net accumulation from when we had 572, which was at t equals 2 hours, to where we're trying to get to, which is 0 back in time. And now I can put S of t dt. There's no advantage for you to flip the intervals of integration here. Even if that were a minus for some reason, there'd be no reason to do that. All right, so let's go ahead and type it in now. 572 plus math 9 from 2 to 0. And our functions in y1, alpha trace number 1 with respect to x. It's working. 577.407 or 408. And what are the units there? Gallons. Now, could I stop there for my final answer?
Yes.
Yeah, unlike above where it asked how much leaked, it was actually interpreting the sign for me. So I had to answer in the positive. This isn't an acceptable stopping thing. Or you could say, so there were initially at t equals 0 hours, 577.47 gallons. And is that a reasonable number?
Yes.
Yeah, if that number had been smaller than 572, you'd be like, whoa, I thought sewage was leaking out, not in, right? All right. It has to be bigger. Okay, and then part C, write an integral equation that gives you the amount of raw sewage in the tank at any given time t. There it is. They're defining the function now for us. A is the amount of sewage, S is the rate equation. So this is again going from the concrete example above to now the abstract below. So instead of calling it sewage now, I'm going to just call it A of t. It's going to equal the initial amount, which was 572, plus the integral from 2 to what?
Wait, isn't the initial amount though
577. No. Again, by initial here, we don't mean well, when I say initial amount, I mean the initial value. I mean the value that we're given initially,
Okay.
not at t equals 0. Okay. I'm always going to use the point that they gave me. Okay. Since I know the value now at 0, I guess I could go from 0 to whatever and use 577.407, but that's a rounded number. Okay. So we're using the term initially here in two different ways. Initial condition is just whatever point you're given. Okay. Initially corresponds with t equals 0. So just like we used up here, Hank, the 572 and corresponded with t equals 2, same thing here. The amount at any time t is now 572 plus the integral from 2 to t of now s of t. But I'm not going to write s of t. I'm going to use the actual equation. Negative e to the square root of f, good, f df. We don't often get to use f as an independent variable, do we? So might as well take the opportunity to do that. What's that? No, for if you're representing this as your final answer, you don't want to have any abbreviations in there. Yeah, you want to have the actual values and the actual expressions that are the functions when they're asking you to write it as your final product. On the intermediate, feel free to do that. Okay. You have to. Yeah. Why do we have to? Because I don't want to have any confusion now. When I do f of a number, I want to make sure that the only number we're changing that is a variable is that top interval of integration. I don't want the integrand to have any part of it, right? So now, retroactively, I could call what I did on part B, I could call it what? A of 0, right? A of 0 would be what I started with at t equals 2, 572, plus the integral from 2 to that same number 0 of s of t dt. And I can use s of t dt above because a of 0 is, we're not defining what the variable is there. So you have to change the variables. Does that make sense? Why again? We clearly want one independent variable. And in this case, we want it to clearly be the upper limit of integration. Yes. A of t equals what?
A of n, just to like switch it up.
They told you to use A of t. Yeah. Yeah. Really, let's save that for the math party, not for the AP exam, right? But yeah, you could call it A of n equals 572 plus the integral from 2 to n of negative e to the t dt. But not if they call it A of t. You can still call it A of f. Don't toy with the math gods, right? When their fate is in your hands, or vice versa. I said vice versa. Yeah, yeah, yeah. That's the illness talking, Hank.
What?
That's my illness talking. Yeah, my head is really congested. I've got like foggy head. But y'all are here to help me. We're a good team. We're a good team. What?
You got better emails
Uh, number 21.
now.
Yeah, it's gonna work out great. What? Oh, we need to do the next part. What? Oh, no. Yeah, it says write an L equation that gives you amount at time t. So there it is. Right? There it is. So that's exactly what we did on part B, but on part B, we did it for a specific value. Now we're generalizing it. Okay. Any other comments on that one? All right. At the start of Christmas break, example 21, here's another nice application. I wrote this one. So let's see. I'm not saying it's autobiographical or anything, but calculated per minute. At the start of Christmas break at t equals 0 days, a man weighed 180 pounds. So now, Hank, and I only say Hank because you brought it up. Now, our initial condition is corresponding with the initial time, right? Right. T equals 0. That is nice when that happens, right? If the man gained weight during the break, and I'm not mentioning any names or even saying that it's me, okay, I have a weakness for fruitcake, and I do love my Aunt Janice's fruitcake. Yeah. She calls it date loaf, but it's got cherries in it. It's good. At a rate modeled by this. Now notice in this case, the rate equation is W prime. That's fine. You can call it whatever you want. 10 sine of pi t h pounds per day. Hey, notice that the rate at which I gain weight is a sinusoid. I gain weight at an oscillating rate, right? It's not even a consistent rate. Pounds per day. There you go. So let's look at pounds per day real quickly. If I were to integrate pounds per day, I get what unit? Pounds. And if I differentiate pounds per day, I get what? Pounds per day squared. Yeah, good. Part A, what was the man's weight in pounds at the end of the break? 14 days later. Show your integral setup and don't judge. Okay. What was the man's weight? Okay, so in this case, I know I'm going to need the integral. Do I need the initial weight or not? Do I add that to it or not? Yes, I'm not just asking for his net change in weight. I want to know what is he at this moment. So it's going to be his initial weight, which was 180, plus the net accumulation from when he was 180, which happens to be 0 now, to 14 of your rate equation, which now is W prime of t dt. So there's your setup. That would be worth 2 checks. Let me go to the y equals now and type in W prime. It's 10 sine of pi times x divided by 8. That's a good enough way to do it. And I go back to the home screen. And now I type it in underneath there, 180 plus math 9 from 0 to 14 of my equation, alpha trace number 1 with respect to x. Boom. 187.458. What are the units? Pounds. Now, does this mean that this person only gained 7.458 pounds over the break? Yeah, it's oscillating. That's only his net accumulation. This guy could have started at 180, ballooned up to like 280, and then came back down to 187 at the end of 14. This doesn't necessarily mean that he'd only gained 7 pounds. All right. All right. Before I do part A, I want to add this question in there. Let's call this A2. What was the man's average rate of weight gain? What was the man's average rate of weight gain from t equals 0 to 14 days? Well, I'm not asking for his average weight. The rate of change is usually the derivative. But the question now is when I'm trying to find his average weight gain rate, I'm trying to find the average W prime. Yes. W prime is his rate of change of weight. So here, I'm not trying to find the average rate of change of W prime. That would be like the average acceleration of his weight. I want to figure out the average Y value of W prime. Is that the integral over the width or the difference quotient? Difference quotient. No. Difference quotient is average rate of change. Average rate of weight gain, if it were the difference quotient, would give me pounds per day per day. I want my units to be pounds per day. I want the average of that function right there. That's the average value. So it won't say use the average value formula. You're going to use the units that are given. What is his average rate of weight gain? W prime is his rate of weight gain. I want the average of that Y value. That's the integral over the width. So here it is. The average is going to equal the integral from 0 to 14 of W prime of t dt over 14 minus 0. Integral over width. All right, now back to the calculator. I'm going to go alpha y equals, boom. And then I'm going to do in the numerator, math 9, from 0 to 14, alpha trace number 1 with respect to t, or x, all over 14 minus 0. What the heck? So this is 0.532, and the units are what? Pounds per day. Yeah. So if you had to write a sentence with units, you would say from t equals 0 to t equals 14 days, comma, the man's average rate of weight gain was 0.532 pounds each day or per day. Okay. On average, he gained a half pound a day on average. Okay. If they had given me the equation for W, what was his weight at any given time, then we could have figured out his average weight by doing the average value. But that was the rate equation. All right. Part B. This is a really good one as well. I like this. All those questions that we did back in like 3.2 and 3.3, where we're finding local max, local mins, and the EVT absolute max mins, we could do those now with integral equations like we did yesterday. At what time was the man his heaviest during the 14-day break? Heaviest. That's a superlative, right? Optimization. Yes. Now, is this a closed interval question or a non-closed interval question? Do we have endpoints here? Yes. So in this case, we could use the EVT as a way to not only find the values, but to justify. All right. Now let's go ahead and do this. Before we do that, let's go ahead and do this. Let's write an equation for the man's weight at any t between 0 and 14. It didn't ask us to do this, but that's what we did up above on part C. Now, it didn't give us a name for that. Like above, it told us to call the amount A of t. It doesn't need to give us a name in this case because the rate equation was called W prime. So we're going to call the weight at any given time just W. It's going to be the starting weight, right? We're going to use what we did on part A up above as a template, 180 plus the integral from 0 to 14. I'm sorry, 0 to t, my bad. 0 to t of, now W prime of t, I first have to type in the actual expression, which is 10 sine of pi t divided by 8 with respect to t, but I can't use t. So what variable?
L.
We've already used L. How about N? I'll use capital N. DN. K works great too. And again, why does it have to be a separate variable? Because t is my independent variable, and I don't want there to be any confusion. It's just the upper limit of integration. So if it didn't ask you to do this, I would probably still write that equation. Probably still would. All right. And then if you want, I wouldn't do this, but retroactively, then the first, what we did on A, you can now call it W of 14. That's what we found. Okay. But the reason it's kind of nice to do it for part B is because we can use the EVT. I now want to know what was his weight at 0, what was his weight at 14, and what was his weight at any critical value on the interior, right? So how do we find critical values of a function? We take its derivative, we see where it's undefined and or equal to 0. So now that I've called it W of t, the derivative left side is W prime. And let's just check. What's the derivative of 180? 0. And now what's the integral from a plain old constant to a plain old t? It's going to be the integrand, 10 sine of pi t eighths. And this is your chance to verify. Is that in fact the W of t they gave us? Yeah. Well, that's t right there. Yeah, that's t. When you take the derivative, it goes back to the original variable. All right, now it's a calculator question. I want to know where this thing, it's never undefined, so I want to know where it's equal to 0. So now, if you go to your calculator, do I have that typed in already in Y1? Yes, so I want to know where the x-intercept is. So now I'm going to go to my window, and since I'm only interested in the 14-day period, my x-min is 0, my x-max is 14. Negative 10 to 10 for your y's is okay, but remember, I like to stretch it out. Negative 3 to 3. That keeps the x-axis in the middle. All right, and now we're going to graph 0 in Y2. That's typically what we do. And we hit graph. Now again, notice we're graphing the rate equation. There's only one critical value. Let's find it. Second trace, number 5. Enter, enter, enter. So underneath there, we'll put t equals 8, and the units are days. And I know that's in my interval because I found it graphically and my table was only set up there. Now, if you're going to justify this using the EVT, we now have some calculations to do, don't we? I need to figure out what his weight was at each of these 3 times. So let's go back to the home screen. Did I already find one of them? Yeah, I already know what W of 14 was. So let's write it over here. It was 187.478. 458, sorry. And do I also know 0? Yeah, that's what they told us. He was 180. So really, there's only the one to calculate. And let's do it. 180 plus math 9 from 0 to 8 of alpha trace number 1 with respect to t or x in this case. And whoa, 230.929. Right, I know. Thank you, Aunt Janice. All right, so now by the EVT, one of these is the max, one of them is the min. And now we answer the freaking question. It said, what was his weight during this time? So now we'll say, so the man was heaviest at t equals 8 days. Okay, and we wouldn't have to justify because that is the justification, right? The EVT. And then you'll say then at this time or at which time? At this time, comma, he was 230.929 pounds, LBS for Libras. All right, now that's one way to justify it with the EVT. What if we didn't even want to write this equation W of t? No big deal. I could have taken the derivative, the rate equation, and set it equal to 0. And look at the graph. This is our relevant domain. You could tell that that x-intercept is a critical value, obviously, because it's an x-intercept. But you could tell that it's a local max or local min also from what the derivative is doing on either side. This has a derivative that's changing from positive to negative. anytime a derivative changes from positive to negative at a critical, or sorry, a sign, a y value changes from positive to negative at a critical value, the function whose derivative represents has a local max there. But this is global maximum that we're looking for. So we can turn it into a global argument, right? So you either justify it this way, we'll call this justifying the first way, or it didn't ask you to justify, but if you had to, you could say this without even knowing what his weight was there. You could say, man is, y'all write it. Y'all write it. I'll get the phone. Y'all write it and I'll catch up with you. Man is heaviest at t equals 8 days because w prime of t is greater than 0 for all t on the interval from 0 to 8, and w prime of t is less than 0 for all t on the interval from 8 to 14. That turns it from a local maximum into a what? A global maximum on our relevant domain. So that would be probably, I don't know if that's an easier way to justify, but notice now, since I know for sure that's the one I want, had I not found W of 14 yet, I wouldn't need to find it, but I would need to come back now and find W of 8, kind of doing something with, like I did similarly on part A. All right. Yeah, sure. In other words, instead of saying immediately to the left of 8, the derivative is positive, and immediately to the right of 8, the derivative is negative, which makes it a local maximum, the derivative is positive everywhere to the left and negative everywhere to the right. So it's a global maximum. Good stuff, right? Good stuff. I agree. Yeah, so really this guy, he wasn't just gaining slowly the whole time from 180 to 187. He ballooned up to 230. So he gained 50 pounds, right? In only 8 days. But maybe, you know, just as impressively, then he loses 40, almost 43 pounds in the next 6 days. This can't be good for his, I mean, this is like, who's the guy that lost the Hollywood actors? They can always gain and lose weight pretty quickly, but Christian Bale, my gosh, if you've ever seen The Machinist, ugh, you know, and then he played Vice President Cheney in a movie where he was like super chubs, right? Yeah, or Batman where he's super buff. So anyway, I always wanted Christian Bale to play me in a movie. So the question is which version of me does he play? You know, slim, trim, fit guy or super chubby guy? All of the above. That's right. As long as he has 14 days. That's right. Okay. Super important section. Super important section. Almost as important as the next section. This one has a lot more theory in it. The next section. Let's have a cool down activity. Let me give you a cool down activity. Yeah. You already cool. What would be the limit as x goes to 0 of the integral yeah, from 0 to x of let's see, cosine of t dt all over x squared. All right, go ahead and do that. I'm going to pause the recorder, but I'll give you 1 minute, 2 minutes. I'll give you 2 minutes. It's 1 o'clock now. I'll give you till 1:02, and then we'll go over it on Mark. All right, I don't need the calculator for this. I'm evaluating a limit. Yay, I love limits. Never not first. Off to the side, I get the integral from 0 to 0 of cosine of t dt all over 0 squared. Let's evaluate that. What's the integral from 0 to 0? 0, because I don't go anywhere. And what's 0 squared? 0. So, hey, this is an indeterminate form. Guess what we can use when it's one of two independent forms of quotient style? L'Hopital's rule. Let's lop it. And thanks, Johann Bernoulli. The limit as x goes to 0 of the derivative of the top. Hey, the derivative of the integral from plain old number to plain old x becomes plain old integram, but now as a function of x, all over the derivative of x squared, which is 2x. Now I'll plug in and I get cosine of 0, which is 1 over 0, which is dne. Yeah, darn it. This is not what I wanted. But hey, do this one real quick. This one is dne. What if this were cosine of t or sine of t up here instead of cosine? That's what I intended. Crap. You would still get 0 over 0, right? That's what happens when you make them up too quickly in your head when you're on congestion medicine. This would be sine of t down here, right? Now that you get sine of x, now what do you get when you plug in? You get 0 over 0 again, don't you? You get 0 over 0 again, don't you? So now we can do L'Hopital's rule again. Lop it, or you can use what we memorized, but you probably forgot that. The derivative of the top is now cosine of x, and the derivative of the bottom is 2. And now by direct substitution, cosine of 0 is 1. It's sine. I switched the top to sine. Yeah. No, the derivative of sine, the integral of sine is negative cosine. When you take the derivative, if it has co, it's negative. So the answer is 1/2. This is another time where the second part of the fundamental theorem shows up when you're doing L'Hopital's rule. Okay, this is a really good question. All right, have a great lunch. Again, we finished 5.3, the worksheet, or 4.3, the worksheet's not due, but yeah, we'll start with the next section. We'll probably have to test next week too, and quiz, or one of the others.